need to say to convince them. If you don't live in the U.S., or if you live in the U.S. and you're not happy with the political regime, then you really need the ability to speak anonymously and receive anonymously and publish anonymously, or otherwise people are going to stick you in jail for otherwise reasonable moral things. If I'm talking to feds, then I say, you guys need to do open source intelligence gathering. You guys need to be able to look at websites and communicate back to your home base in a way that other people cannot monitor and identify. If you've got an agent in some foreign country and he needs to talk back to CIA home base, you need a way to do that that doesn't reveal that he is talking to CIA home base. If you're a corporation and you believe that your firewall will solve all of your information leakage problems, you might want to rethink that. You can set up a VPN, you can encrypt everything. If you spend a whole lot of time talking to a competitor and then suddenly a news release comes out, maybe people have been watching all of that traffic and thinking, he's probably going to do something with that other person that he's talking to. Or maybe if you don't want to release the fact that you're about to merge with a company or go out of business or something, traffic analysis can leak a lot of information. So if you think that your VPN and your encryption will solve it, you might want to reconsider. So the one that makes the most sense for me, people are collecting information all the time right now. DoubleClick is figuring out everywhere I go. Amazon's figuring out everything I buy. They're making recommendations to me. They're building profiles of me. And these profiles are getting better and better. Do I really want them to know everything I've ever been interested in? Do I really want an employer in 10 years to say, well, yeah, but you bought that book on Amazon a while ago. Are you sure you want to work with us? I really don't want an employer down the road to say, well, I looked at your genetic history and I don't think you're suited for our company. If that doesn't scare you, think of the fact that it's happening to your kids right now. They've got really no control over it. What's going to happen in 40 years when they've grown up and everybody knows everything about everybody? Okay, so hopefully that convinced you that maybe this is relevant. I'm going to jump into some actual anonymity systems, but before I do that, I want to make sure you know that you should jump up and argue with me whenever you want to. If you've got any questions, this will be a much clearer talk, something that doesn't make sense. And I enjoy arguing with you. Okay, so the first option you've got, a single hop proxy. Basically, this is something like the Anonymizer or SafeWeb or what Zero Knowledge I think is working on now or something like that. You've got one machine, or maybe several machines, but you've got one company, and people go to that company and say, please strip off where I came from and do this web request for me, and send this mail for me, or something like that. It's by far the easiest to deploy. You just set up a proxy or a server or something, and you're done. It's by far the most popular in terms of people using it because it's easy to make it efficient, and it's easy to understand the concept of, oh yeah, I'm trusting some guy named Lance, and he's going to protect my anonymity. He's going to keep people who want to find out where I'm going from finding that out. On the other hand, it's a single point of failure. If that company goes out of business, changes its business policy, decides that maybe it doesn't want to enforce anonymity this way, or maybe the Fed that just showed up with a subpoena is actually worth talking to and working with because maybe they need something else from the government. So there are legal issues and technical issues for why you may not want to trust just one hop. Okay, soon I'm going to tell you about the concept of using multiple hops for your anonymity system. Before I do that, I'm going to give you a couple of pieces of terminology so we can know them down the road. In the research world, we always think about the adversary, and the adversary can have many different characteristics. Maybe he joined the network and he said, oh yeah, I'd like to run a Mixmaster server for you. I've got this wonderful T3 network in Maryland, and I'll set it up for you. It'll be great. Or maybe he just deployed something named Carnivore, and he can watch all the traffic going by, but he doesn't actually own any of the nodes. Maybe he's passive, meaning he just watches what goes on. Or if he's active, he actually compromises systems, injects mail in that wasn't going to be there otherwise. He delays mail, something like that. He could be local. He only owns a few nodes in the system. Maybe he's a local ISP that monitors the network. He could be global. Maybe he's Sprint and BBN and FBI and a number of other groups combined, and they're all getting together to say, wait a minute, who was this person who just said that George Bush is being a bad president? We've got to track him down. From an analysis standpoint, we look at static adversaries, where basically you look at the system and you say, well, he owns that, and that. And is our system going to be robust if that's the case? Or he's an adaptive adversary, where he starts out owning those four, and then he says, well, wait a minute, this is important. I've got to figure out who sent this mail, who received this mail, where the file is stored, something like that. I'm going to pour a lot of resources in, and I'm going to start compromising new machines. So we look at how quickly can the adversary compromise machines, and is it quickly enough that we should be worried about it? Okay. So if you're at Lunchdoc, you already know pretty much about Mixmaster. I'll give you a brief overview from the beginning. A mixed node. David Chaum came up with the concept of a mixed node 20-some years ago. The basic idea is you've got a single node, and messages come in, and they get decrypted based on that node's private key, and then they get batched, so many messages hopefully come in at the same time, and then they get reordered and batched and sent out. And you cannot look at a message going in and a message going out and correlate them. So it's important that messages are all the same length, otherwise it doesn't matter if you decrypt it, because the one that's really long is probably the one that's really long coming out. One of the interesting characteristics of this, in order to batch, in order to get enough messages in at once, you're going to want to delay a lot of the messages. And that means we really can't use the system well for low latency things like web browsing and that sort of thing. So a mix is really better suited for email and that sort of thing. I'll get into that a little bit more down the road. Okay, so the next building block, a mix cascade. If you take several mixes and you put them in a row, then you have, first of all, it slows down a little bit, but second of all, you don't have to trust the node that you're using. You don't have to trust that one mix to not be compromised, to not be leaking information about, oh yeah, that message came from that guy over there. So the idea here is you use several nodes in a row, and a batch of messages comes in. I'm going to try attaching this to my shirt. How's that? How's that? Okay. A batch of messages comes into the front of the cascade, and maybe it batches at 100 or something. So you've got 100 messages, and it decrypts the 100 messages, and it reorders them, and it sends it to the next node. Now, if that node were honest and wasn't leaking correlation between messages coming in and messages going out, then you've got your anonymity. You win. If that node is not honest and it's owned by the adversary, then you get to the next node. And the next node takes the 100 messages, decrypts it, batches it, reorders it, sends it on. And as long as one of those nodes in the cascade is honest and is not leaking information, then the adversary does not know who sent the message to who. So the key point here is that the anonymity comes from having more users. It comes from having a large batch size. It doesn't matter how many nodes we put in a row, as long as at least one of them is honest. It comes from having lots of people using it, lots of messages. On the other hand, it assumes a global adversary, because a cascade is generally a fixed path of nodes, and it's got a node at the front and a node at the back. And if everybody knows what the topology of the network is, then if you're the adversary, all you have to do is go stick a sniffer at the front and go stick a sniffer at the end, and now you know who is sending mail in and who is receiving mail. And in a lot of cases, you can just bypass the actual anonymity system itself and start looking at, well, this guy probably was sending mail to this guy, and it's likely that he was. So there are a number of interesting attacks that come in for the cascade model. One of the interesting ones is if I'm the bad guy and I'm not just passively trying to figure out which message was which, but instead I'm saying, okay, I'm going to take the batch of 100 messages and I'm curious about that one that Alice just sent. I'm going to throw away 99 of them. I'm going to insert my own messages that go to people I know, and now I'm going to let the batch continue. And the 100 messages continue just as normal, and they get to the end, and 100 messages get delivered. 99 of them go to people I know, and one of them goes to the guy I didn't know about, and now I do. It's pretty difficult to make that sort of attack go away. So there are people in Germany who've actually deployed this. They've got a thing called web mixes, which is a mix cascade, and they have, I think, 4 or 5 nodes, and they've got quite a few users. If you Google for Java Anon proxy, then you'll find it. They have lots of users in Europe. They have very few users in America. So their usage patterns basically go like this for during the daytime in Europe, and they don't have much use other times. So they'd be happy if they've got more users over here, because that would spread it out a little bit more. Okay, free route mixed networks. So the user picks a path through the network. This is a big difference. It isn't, there's a topology, it's fixed, you use it. Instead, there are a whole bunch of nodes, and you say, well, I'll pick that one, and that one, and that one, and that one. And maybe you pick them based on how much you trust the operators, if you know the remailer operators. Maybe you pick them saying, well, this one's in this jurisdiction, this one's in that jurisdiction. They can't all get together and figure it out, because maybe I used a remailer in Iraq, and Iraq will say, no, screw you, I'm not gonna talk to your government. So the goal is to hide the message's path. That's a critical difference in the approach to getting anonymity between the cascade model and the free route model. So if you have a global adversary in this sort of situation, and there is no dummy traffic, then Alice sends mail, and maybe it works its way through, and maybe there's a node that waits a little while until there are enough messages coming in before it batches and reorders it. But in a lot of cases, you can look at it and you can say, well, Alice sent mail, and then somebody else sent mail, and then Bob received mail, and then somebody else received mail, and those are the 2 users who were in the system at that point. That's not good if you want anonymity. So one approach is everybody sends lots of dummy traffic all the time. And hopefully that will confuse the adversary, because it wasn't just Alice and this other guy who sent mail, it's 500 people who seem to have sent mail. It's difficult to figure out when to send mail, how much dummy traffic to send, where to send the dummy traffic, that sort of thing. So it's unclear if that's actually going to give you as much advantage as we hope it will. Another approach is if you've got a lot of users, then you've got a lot of Alices, and hopefully that'll help too. So Mixmaster is the example for that, and hopefully you heard about it a little bit before. You'll hear about it more in a couple of days at DEF CON. Okay, crowds is a very different approach. Before I've been talking about there are nodes and there are senders, and the senders want to make it not known that they sent messages through the network to the other side. Here you have a whole bunch of people participating. All of the nodes are users, and people are trying to web browse anonymously. And what they mean by anonymously here is there are 50 of us running this crowd, and you don't know which of us was the one that just did the web request. The way it works is when you want to do a web request, you flip a coin, and if it comes up heads, then you send it to somebody else in the network. And if it comes up tails, then you go directly to the web server. And if it comes up heads, then you go to the other guy, he flips a coin, comes up heads, goes to a second person, comes up tails, goes to the web server. And you can weight the coin however you like to figure out, to get a path length that you expect. And so the idea here is the web server has no idea where the request actually originated. He knows that it came from a member of the crowd, and he can say, you just did that web request, and the guy can say, well, no, it came from somebody behind me. And even the person who originated it can say, well, no, it came from somebody behind me. So it's plausibly deniable that any given person in the crowd made the web request. On the other hand, the crowds model itself doesn't do any mixing. It doesn't do any encryption. So if you're a global adversary, then you basically can say, well, no, I was watching you the whole time, and the request did not come from behind you. You were the one who made it up. So crowds is a really good approach for certain situations. We find this same idea cropping up again and again in various peer-to-peer systems these days, like Freenet and so on. Basically, you pass your request around, and the idea of passing it around hopefully means that nobody will know where it came from. Okay, did I just, yes I did. Zero knowledge. I'll talk a little bit about this. We've got a couple people in the crowd, so hopefully they can argue with me and question.
So I was wondering, in crowd, you're not worried about just the anonymity that anyone who could possibly send a message, but you're worried more about probabilities and sort of, there's certain people maybe in a crowd who are more likely to send a message than others because of the way that it gets transferred.
Yes. So the question is, you've got 100 people in your crowd, and the web request went to bonsaikitten.com. Most of those people in the crowd won't want to have gone to bonsaikitten.com, and it happens that a week ago somebody went there also, and you know who he was. So you're pretty sure that just because there's a plausible deniability there, you're pretty sure you know who it was. Yes, that's a really nasty issue. The probabilistic approach is it's one that a lot of people try to use, and in a sense, it's good. I mean, you can still say, well, yes, you think it was me. It seems like it was probably me, but you can't prove it. So in the US, that's kind of nice. In England, that's really nice, because England keeps passing these laws saying things like, well, if you've got an encrypted thing and you can't decrypt it, then you're guilty. You're guilty of anything we think it might have been. So if you can get some plausible deniability in that sense, then it's really nice. You brought up another point of data anonymity versus connection anonymity. If you use crowds and you go to a web server and you type in your name and credit card, it doesn't help. Crowds does not help in that situation. And a lot of people do that sort of thing. Not even in terms of, here's my name and credit card, but I'm going to have a pattern of web surfing which is unique to me. And there are 100 other people in the crowd, and they all have their unique web pattern. So if you actually research the crowd, then it becomes not 1 in 100 that you were the person doing it. It becomes some weighted probability based on how likely you were to do that, what you've done in the past, and so on. Did that answer the question? Okay. Zero knowledge. Mixmaster is a high latency system. The idea is you wait a while until you've got a really large batch, and then you reorder, decrypt, send out. Zero knowledge is trying to make that same sort of thing low latency, was trying to make that same sort of thing low latency. So they paid a bunch of ISPs to run Freedom nodes, and they had really good bandwidth, good latency, and so on. An interesting thing here, in Mixmaster, you send the mail. You say, there's this mail here, and I want it to go into the anonymity system. In the Freedom approach, they said, we're going to give you a kernel shim or whatever the appropriate thing is for your operating system that takes every packet you generate, and we're going to stuff it up in a little box and pass it over the Freedom network and unstuff it and then send it off. So the exit node, in a very real sense, is acting like your computer, but they take off the IP address and revealing things like that. So in this case, you really anonymize everything, and that's critical if you want to use all sorts of applications without modifying them, because let's say you've got an application that does a get host by name. It looks up a domain name before it tries connecting somewhere. So if you look up the domain name and that goes directly out, and people say, oh, he just looked up bonsaikitten.com. Then it comes back, and then you make your anonymous connection to somewhere, nobody knows where. That doesn't work so well either. On the other hand, Zero Knowledge tried to market this, and they didn't get enough users to make money enough to keep it in business. It's pretty expensive each month. So there may be a lesson in there, there may not be a lesson in there. We're not quite sure yet. Onion routing. It's very similar to the freedom approach, connection-oriented, which means you actually do a TCP stream to it. I can SSH to an onion routing system, and it will pass my actual TCP stream back and forth. It aims to be fast enough that you can do this in real time. Certainly web browsing works that way. If you want an SSH connection, maybe you're getting 500 milliseconds latency or something. Maybe that's acceptable, maybe it's not. The way it works is you've got a bunch of onion routers set up over the network. It's an overlay topology. And they have long-term TCP connections between them. And hopefully they do link padding enough that it's not quite clear who is starting a connection to who and so on. So the idea is a user, Alice, will, I've got a slide in a little bit that tells all about what I'm about to say, so I'll do that. So an interesting thing about onion routing, it aims for traffic analysis, not traffic confirmation. We're doing a real-time system here, and if you make a request, and then a request goes to a web server, and then an answer comes back, and you get an answer, and all of that happens in well under a second, and nobody else made a request during that second. If you're a global adversary and you were watching Alice and you were watching the web server, then you're quite sure that it was Alice who just made that request to the web server. And we can't slow things down and batch them, because otherwise it would take 30 seconds to load a web page, and that's no good. Another perspective for that is if you are worried about that sort of thing, you should run a node yourself. And then, because there's link padding between each connection in the core onion routing system, then it's unclear when you've made a request. I'll get into that in a little bit. Okay, I'm going to switch over to some slides from last week that we gave to the DARPA project that have some graphics. And this will hopefully explain onion routing in a little bit more detail for people who prefer pictures for understanding things. So you've got your initiator, Alice, you've got your web server, you've got some public network. If you encrypt it, that doesn't hide the fact that you're talking to somebody else, and it doesn't hide your patterns of communication. This happens on, this traffic analysis issue is an issue on the public internet. It's also an issue on military networks, which are supposedly very secure because they use point-to-point encryption. But you can still figure out who's talking to who. And yeah. Okay, so we've got a bunch of nodes on our overlay topology, and Alice is going to be talking to the web server there. So Alice has a proxy. The basic idea here is Alice runs an onion proxy on her machine, and she also has some application proxies, say a web proxy that knows how to talk to the onion proxy and so on. So the onion proxy picks the path. That means that nobody else can know which path Alice chose. In this case, we're doing the same approach as Mixmaster, which is I pick the path, my anonymity comes from the path, and hopefully you can't figure it out. So the way it works is Alice's onion proxy builds what's called an onion. It's a layered encrypted thing, and it's got the message or something similar inside. And at each node, it's got a key that it uses for symmetric decryption. So Alice builds a huge onion and hands it to the first node in her path. It decrypts the first layer and says, oh, I'm supposed to go to node D, and this is the key that I'll be using for all data that you pass back and forth. And then that propagates down through, and then F gets the last part and says, okay, I'm going to wait around for a little while, and hopefully somebody will pass data down through the TCP connection that says where I should connect to. And yeah, the initial proxy knows the onion routing topology. Okay, so this is how data is actually sent. Once we've sent the public key encrypted onion, then we have a circuit that's built on the onion routing network, and there's a symmetric key at each hop, which is much, much faster to work with than a public key. So Alice starts with her data message. She wants to send a packet in TCP that has some actual data in it. So she wraps it up in the symmetric keys, and then she hands it to the first guy. And the first guy says, well, I've got a key. I'm going to take off a layer and hand it to the next guy, because I know where it is. It's part of that circuit that was just set up. So it works its way down, and then at the end, it's the message itself which gets delivered to the web server. And the same sort of thing happens back. The web server gives a packet, and this guy says, well, I've got a key. It's coming that way, so I'm going to encrypt it. So it builds up, and then Alice's web proxy gets it back and says, okay, I need to do 5 decryptions or whatever it'll take, and then I can read the message again. Is that clear? Should I clarify? Ask questions. Okay. feel free to jump in whenever. Okay, so I definitely have, well, we'll start that one again, will we? Okay, so now I'm going to talk about a couple of technical problems in onion routing that I've been working on over the past little while, and I imagine Zero Knowledge has encountered these, and hopefully they've solved them for me. I know they've solved some of them, and this will hopefully give you an idea that onion routing is maybe a little bit hard to do. First of all, there's the proxy issue. Right now, we have an application proxy for each protocol, which means you run a web proxy that knows how to talk to the onion proxy. And we've got an onion proxy. So Alice has to run an onion proxy and an application proxy for every protocol she wants to support through the onion routing network. That's crazy. Nobody's ever going to run all those proxies. We need to come up with some other way. One way to do it would be the way Freedom does it. Basically, you grab all the packets and you shove them through the onion routing network, and then your computer acts as though it's on the outbound end of that. Apparently FreeBSD has a built-in support for that in the kernel, basically a packet redirect. There are some people porting that to Linux and I think Windows. Hopefully they'll get done with that sometime, because I sure don't want to work on that. Now, it may not be that we'll have no users. It may be that we'll have quite a few users if onion routing is taken up by some of the peer-to-peer projects that keep saying, we need anonymity, but it's hard. I've talked to a number of people from the P2P world, and they say, you built onion routing, I can use it. All I have to do is add support to it for my proxy. So we'll see in a couple of months if they'll actually do that. Oh yeah, and I wrote some code. I wrote onion routing a couple of months ago, and it's GPL'd, so eventually the world will get it. There are some complications because apparently every time you write anonymity software, everybody says, oh my god, that's anonymity software. I must own that. That must be worth a fortune. And so everybody's made a grab for it, and I think I've fended them all off. So I hope to give it out sometime soon. If you want it, send me mail, and I'll give it to you. I don't want it on Slashdot yet, though. Okay, so let's chat a little bit more about onion routing in terms of problems. So here's my ideal threat model. I want the adversary to watch everything that's going on, and I want him to own quite a few of the nodes on the network. And I still want to get anonymity. That's a little bit tricky. Okay, so the first issue, link padding, topology. Right now the onion routing system is a clique. Everybody is connected to everybody. And we do link padding. Everybody link pads to everybody. So the idea right now is if you've got, say, a 100 kilobyte connection to each onion router, and there are 10 onion routers, then everybody is sending a megabyte a second forever, all the time. Nobody's going to run one of these things. We need to figure out a compromise at that point. So ideally for anonymity, you should always be padding up to the maximum that you will ever send. For efficiency, you should not pad at all, because that's crazy. So we need to find somewhere in between. And there are lots of different proposals about perhaps we don't need to do any link padding, and when a connection starts, then you broadcast out and you say everybody should raise their links by one connection worth, and we'll do padding inside the actual conversation so it goes at a constant rate of 10 kilobytes or something like that. That's still actively a research issue. Okay, now we get to some of the more fun attacks on onion routing. I described them earlier, timing attacks. If the adversary owns 2 nodes on your path, then he watches the messages go by and he says, oh, well that was 12 data cells, and I just saw 12 data cells over here. And I passed 2 back, and I just saw 2 here. I bet I'm on the same conversation. And if the adversary happens to have those 2 nodes at the front and the back, then he says, well, it's Alice over here and it's Bob over here. I know they're talking because I can recognize the timing signatures. If he's kind of close to the edges, then he can say, well, I'm over here, and I have a pretty good idea how long it takes to go through a hop, so I figure there are 3 or 4 hops in between, and people probably won't use more than 5 or 6 hops in a path, so I'm probably close to the endpoints. I should go ahead and compromise that guy who just opened the connection to me and find out who he's talking to, and maybe he's talking to Alice, and then I'll learn that, and I'll compromise the guy on the other side. And so this requires a pretty strong adversary, of course. I mean, he's watching the network, he owns some nodes, he's able to break into other nodes, and he's able to do that in a time frame where somebody's doing a web request. That sounds pretty hard. On the other hand, if somebody's doing an SSH connection over this, and they've been talking for hours, and they'll probably be talking for several more hours, then you might have plenty of time to do that. So this can work passively. You just sit there and you count packets as they go by and you figure out how many there are. It can also work actively. If I'm the adversary and I own these 2 nodes, then I can find 12 data cells as they go through here, and I can delay them and wait, and now I've got 14. And 14 is an unusual pattern to send, so I send 2, 2, 4, 5 or something, and it arrives here with the timing pattern that I just generated. So I can actually confirm these sorts of things actively. I don't actually have to own any nodes to do this. If I can watch the web server, and I've got a node over here, and Alice sends Alice sends a connection and starts to send data cells, and I flood her link a lot, so her data cells slow down, and maybe TCP has to retransmit. And then I stop flooding, and it goes quickly, and then I flood a lot, and then I stop flooding. And I've induced timing signatures that I can recognize at the web server end without having to own any of the nodes in the system. So, yeah, it's a pretty nasty attack. It's a good argument for not wanting to be robust against a global adversary. Tagging attacks. So onion routing uses a stream cipher on the data. Once we've set up the circuit, then everybody has the key that they've got, and basically we act like a stream cipher. We XOR it, the data coming in, with the stream cipher we've got. Now, if I'm an adversary and I own a node and I'm watching the web server, and I take a data cell, and I just mess up one of the bytes. I smash it, it looks different. And now the conversation to the web server goes there, and one of the bytes is wrong. Maybe it says get index.hqml. And you say, well, wait a minute, there's 1 byte. I tagged 1 byte. Excellent. And maybe there's a more complex approach of this where you take the data packet and you say, well, I'm going to tag that byte, and that byte. And there will be 3 bytes in between here and 2 bytes in between here. And now a funny-looking signature comes out to the web server. So this is a really nasty attack. It's another good argument that we don't want to actually try to defend against a global adversary in this case. The same attack comes up in Mixmaster, by the way, in 2 different forms. One of them is Mixmaster headers only have a hash of the pieces of information for that specific hop. So there are many different headers in a Mixmaster packet, and if I trash a header 4 hops down the road, and then I happen to own the node that's 4 hops down the road, and it receives a message that has had the header trashed, then I can probably correlate that those 2 were the same. So that seems kind of unlikely, because I have to own the node that's 4 hops down the road, and I probably won't. I can also do a tagging attack on the payload of Mixmaster. It depends on the actual encryption approach that you use, but it's easily conceivable if you use a block cipher or a stream cipher or something like that, I can tag 1 chunk of the message, and then the actual mail that comes out says, "Dear Bob, please meet me at," and you can recognize that was the block of the mail that I just tagged from over here, and we can correlate that they connect. So it's usually solved by including a hash in the message of everything that's going on. It's a little bit more complex than that. First of all, you may not want to use a hash because you may want to be very quick, but hashes are pretty quick. You may not know the payload that you're working with. If you're talking about a reply message for Mixmaster, or you're talking about data coming back from the web server, then you don't actually know. If you're talking about data coming back from the web server, that web server doesn't know the keys that everybody else knows. It has no idea how to build a hash that will match correctly. If you're talking about a reply message in Mixmaster, the guy who wrote the reply block is not the guy who wrote the payload. So how on earth is the guy who wrote the reply block going to get a hash that is correct for the payload at every hop? So it's more complicated than that. And there are some fixes for Mixmaster, which I'll be describing in a couple of days. And for onion routing, you're screwed.
Couldn't you mitigate some of those attacks for certain applications, like peer-to-peer and web browsing? If the application is tolerant of inconsistency for short periods of time by caching within the network itself. So not every request from a participant in the network results in a request to the ultimate destination. So say,
Okay, so the question is, can't you make the timing attack not as bad by not always having a message coming out? Let's say you're talking about the freenet model where you always cache the answers as they come back. So when Alice makes a request, it's likely that a node in the path that she chose knows the answer to the request already. So it doesn't have to go to the end. It doesn't have to go to the web server. Yes, you can help this sort of thing, but as far as I can tell so far, there's no way in the general case, or even in a pretty broad case, for you to stop me from being able to induce a timing signature on the connection. Because maybe something's cached, but maybe I'm requesting something that's not cached. And that one's got to go to the web server. And if I can twiddle things so it looks like a new request, then that may be bad also. So, oh yeah, the long-term intersection attack. This is the exciting question in the anonymity research world and has been for a long time. So the issue is, on Monday, Alice sends mail, Bob gets mail. Next Thursday, Alice sends mail, Bob gets mail. Next Sunday, Alice sends mail, Bob gets mail. So we're looking at a set of suspects each time. These are the people who sent mail today. Notice that Alice is in this set. Now we're looking at a set of suspects later on. These are the people who sent mail when Bob got mail. Alice is in this set also. Now I've got another one. Alice is in this one also. If I take the intersection of these sets, I've got a very small group of people who could have sent that message. And there really isn't much that can be done about that. One approach is dummy traffic. The basic idea here, the basic problem, is that people have different behaviors. People have different usage behaviors. And we have to enforce that everybody behaves exactly the same. Basically, in the simple approach, it would be everybody always sends mail every time click, and everybody always receives one mail every time click. This is not really feasible to coordinate, but that would be the ideal case. And some sort of approximation of that would be a nice start, at least. If we could have dummy messages that are sent when you're not online, which means Alice effectively looks like she sends mail every single day. Lots of other people look like they send mail every single day. And maybe they're on vacation some of the time, and somebody else is sending the dummy messages for them. It's a little bit difficult to work the details of that out and still get anonymity, but it's a nice idea. We certainly need to start working on that problem in more detail. Okay, so timing attacks, tagging attacks, all this stuff. We don't want to protect against the global adversary. We don't want to protect against somebody who says, well, I'm watching Alice send messages and I'm watching Bob get them. It's obviously Alice talking to Bob. We want to start thinking about an adversary who owns some of the nodes and can see some of the nodes. And maybe he owns half the nodes, which means he's got a 1/4 chance of owning both of these. And if he owns both the part that Alice is talking to and the part that's talking to Bob, then we lose. But 1/4 is not so bad. And if he owns 1/4 of them, then he's got a 1 in 16 chance of owning both of them. So that's more reasonable, but I'm also very unhappy with that, because 1 in 16 chance of getting thrown in jail is not a very happy probability. So we want to work on that one also. Okay. Now I get to the interesting part of the talk. So that was technical approaches. Are there any questions about the building blocks that I described, or the problems that I described, or anything like that? Yes?
I think you were just talking about was for a low latency system. What about latency? Is that true for a high latency system that I'm worried about having the endpoints compromised in that situation?
So the question is, I was just talking about long-term intersection attacks, or intersection attacks in general, and I was talking about them in the context of onion routing, a low latency system. And it's obvious Alice sent a message, Bob got a message. And you can correlate that really easily. And over time, Alice sent a message, Bob got a message, Alice sent a message, Bob got a message. It's very clear. In a higher latency system, one of the goals there is to make that attack not possible. The goal is that we delay and we batch, so Alice and 45 people sent messages, and Bob and 45 people got messages. So on looking at a single mail you send, Mixmaster does a lot better, because it delays, and it isn't going to be within a second that the request goes to the web server. It will be within a day or two that the message gets to Bob. And if there are lots of users, then there are going to be a whole bunch of people who've sent mail in that day, and a whole bunch of people who've received mail in that day, and it will be very unclear that Alice was the one who sent it and Bob was the one who received it. So that's great if Alice only sends mail once. But if Alice sends mail and Bob gets it within a couple days, and then every Monday Alice sends mail and Bob gets it within a couple days, and then Alice goes on vacation and Bob doesn't get mail, that's pretty suspicious. So the long-term intersection attack comes up in different ways, but it's the same fundamental problem, and nobody really has good answers for it. Other questions? Okay. So anonymity is hard for economic reasons too. I'm going to basically go through and argue that it's pretty difficult to get these things deployed and used, and if you do, then you're probably not getting much anonymity anyway. So anonymity requires inefficiencies in everything you do. Anonymity requires making your users unhappy. My web request is slow. My mail doesn't go through for 5 days. My mail sometimes even gets dropped because your reliability system isn't very good. All of these make your users less wanting to use the system. So you're only going to get the users if it's that unusable and that uncomfortable that really, really need it. Unlike encryption, Alice can't say to herself, well, I need anonymity on this message, so I'll apply the anonymity software to the message, and then I'll send it, and Bob won't know that I was the sender. You need a lot of people at once, plus an infrastructure, to say, we can provide anonymity, and the more people who use it, the more anonymity it can provide. It's the network effect, the same sort of concept you get when 5 people have bought a fax machine. There's no point in owning a fax machine because you can only fax these 5 people. But if you have lots of people buying fax machines, then suddenly you've got the momentum, and you're on your way to having a system that lots of people are familiar with and usable with and reachable and so on. So, okay, so the key point about these anonymizing systems, other people are providing your noise. You need other people in order for your anonymity to work. And the more noise, the more other people, then the better it is, the more anonymous something that noise is. An interesting point here, you're always better off going where the noise is. So I can tell you these beautiful, technically sound ideas about these mixed nets that delay for 6 hours at each hop, and they batch a whole lot, and there's a lot of dummy messages, and it's great. It's technically beautiful. Nobody will use it. If nobody uses it, then it's worse than the anonymizer, which is simply one hop and has 20,000 users a day or whatever they've got. So it's a really critical trade-off here between, is this system technically good, and am I getting enough noise in it to actually have it be useful? More users is good. If we've got high traffic, we've got a lot of users, then we can start having our batching periods be smaller and smaller because we've got our 100 messages pretty quickly. And at that point, we get better performance. Your mail goes through in 2 hours, not 6 hours. If we've got better performance, we've got more users, we've got more traffic, we've got better performance. It goes through in 1 hour, not 2 hours. So as we attract more users, then we can get the system to be faster, more efficient, and we get more anonymity. So that's a good sign. I mean, we've got 2 things that work together to actually make the system useful. On the other hand, we've potentially have trust bottlenecks. We've got a bunch of different nodes in the path, and each of those nodes we've got to trust at least somewhat. The idea that Chum had originally was you've got a set of messages in your path, and as long as one of them is honest, you're fine. Recent anonymity research basically says that if people are behaving differently and sending messages at different times, and you can watch everything, then you really aren't getting what you want out of just one node being honest. You want quite a few of them to be honest. And nodes that get lots of traffic need to be more trusted because they're handling a proportionally larger amount of the network. An interesting point here, an interesting note, is that if I am wanting to be a global passive adversary, or as close to global as I can, I should run a bunch of nodes. I should provide really reliable service. So people say, I need to send a Mixmaster mail, and I want it to get through. So I'm going to use that one in Maryland, because it always gets through when I send it through the one in Maryland. And while you're doing it, you might as well knock down the ones in Italy and Australia and the ones that you don't really like, because then they'll have low reliability. And people will say, well, I never use the one in Italy because it never works. So suddenly you've got your users sending messages through the one in Maryland, the other one in Maryland, and the third one in Maryland. And you're doing a lot better at being able to observe the traffic at that point. So right now, Mixmaster and Mixminion Will has a set of statistics servers. You go there, you say, these are the 30 or 40 or whatever remailers you've got right now, and I want to figure out which ones I should use, which ones are most reliable. We have no way of figuring out, so the problem is, you've got a couple of nodes at the top. They're very reliable. Reliability has nothing to do with whether they're leaking your data. And that's a fundamental issue that we have to figure out, because right now you've got stat servers, and you obviously pick from the ones that are at the top because they're best, whatever best means. In this case, best really doesn't mean they're not the adversary. It just means they'd be happy to pass your messages along, and the adversary would probably be quite happy to pass your messages along, because then he gets to read them. Okay, so this slide is my argument that the anonymizer is not enough. Strong anonymity requires distributed trust, requires multiple nodes. So let's say I'm the CIA, and I want an anonymity system. I want to be able to web browse anonymously, to send mail, to have people talk to me anonymously. I need this infrastructure so I can perform my duties. I'm going to run it myself, of course, because if I don't run it myself, I've got to trust some other guy to do it. Okay, so now I've got this infrastructure, and I do my anonymous web browsing, and all the users on the system are CIA agents. And somebody looks at the infrastructure, and they say, well, a web request came from that CIA anonymizing system. Those CIA agents, they're always thinking they're getting anonymity, but they're always CIA agents. I don't care which one it is, but it's the same group that keeps doing the request. So you've got to have other people using your system. This is a difficult thing to get the government to understand at this point. If we need to build the infrastructure which you say you need, then we must let ordinary people use it. We must let soccer moms talk to web browsers anonymously through it. Because without those users, we're not going to have any sort of protection. On the other hand, so you've got to carry traffic for others to protect yourself. If you carry traffic for CIA agents and soccer moms, then they're going to be going to different websites. And people will say, oh, that's the anonymizing system that has soccer moms and CIA agents. And I'm a government somewhere. The soccer moms aren't looking at me. It's the CIA agents who are looking at me. So you need to carry traffic that looks kind of like yours. And that means you need to carry traffic from people who have similar paranoia as you do. And they're all sitting there thinking, well, I'm the FBI. I've got to run my own infrastructure. How else do I know it's secure? So you need to carry traffic for other people, and they need to trust you. So both of you run an infrastructure, and you both trust each other less. And if you extend that, then you have a distributed system where the trust is distributed. And you have to support other people coming in, and you sort of trust your system, and you sort of trust everybody else's, and you hope it works out. Okay. Can we run this distributed system by paying people? Or getting money from people and having them pay for it? Maybe. It didn't work out so well for Freedom, but they paid quite a bit per month for it. It may be that if we don't have to pay enough and don't charge as much or charge more or market it differently, or I don't know, if we do something different or we're in a different decade or who knows, this sort of thing might work. On the other hand, most venture capital right now are saying, well, look at those companies that failed. We're not going to fund that. No way can you run this thing for money. Can we get volunteers to do it? That's the Mixmaster approach. They say, well, we need an anonymity infrastructure, and here's our software. Please run it for us. Please keep it up. It's a good idea. I hope it works. I'm still kind of hoping it works. There are a couple of issues with this. One of them is liability. If you run an exit node and somebody sends a death threat to George Bush out of your exit node, and you get a call from the Secret Service, and they are maybe nice, and then the FBI argues with you for a while and throws you in jail while they figure out what Mixmaster is, that's not so nice. You'll have a lot fewer operators when that sort of thing starts happening. So there are very few people who are actually willing to run exit nodes. And this is bad because now it's not a free route topology. Now it's a funnel topology. A bunch of people are willing to accept messages, and they all go to the 4 nodes that are willing to be exit nodes. So the adversary wanting to observe messages goes to the exit nodes, and he only has to plant 4 sniffers, and now he watches every message coming out of the network. Having a whole bunch of volunteers might work. This is the freenet approach. They can't catch us all. They can't bust us all. We'll just run 100,000 nodes and we'll conquer the world. On the other hand, if you took a couple of those nodes and you threw them in jail publicly, loudly, and left them there, suddenly you'd move from 100,000 to 20,000. And then if you did some good lawsuits against some of the other people, then a whole bunch of other people would chicken out. And soon you'd be left with very few nodes. You'd be left with the people in Haven Co. and the people who are crazy enough to keep running remailers and that sort of thing. And now you're back to 40 nodes. So that's a hard problem, and we're still working on it. We can allow people to set individual exit policies. So it isn't black and white. I'm a middleman node, I don't do any exiting, or yeah, you can send mail to George Bush, no problem. Maybe you can say you can send mail to anybody at mit.edu because I'm the mit.edu remailer. Or you can set some sort of policies like that. But if you don't have very many open relays, open nodes, open exit nodes, then you're going to run into problems where you don't have the topology you think you have. Okay, pseudo-spoofing. You can take volunteers. There are 40 remailers or something. What if some nice agency in Maryland said, let's run a remailer. Let's run 50. And let's find an agent in Idaho that wants to run one, and some great hacker in California that we just paid $10,000 to act like a hacker and run a remailer. And are half of your nodes run by the same group? Who knows? How do you know that? We could set up a global public key infrastructure that identifies every person. We'd have a national ID, and you'd present your national ID and say, I, Roger Dingledine, wish to run a remailer, and I've only run one, and here I am, and here's my pledge. We could do that, but it'll never work. We could do decentralized trust flow algorithms, very similar to the PGP web of trust, where you've got a bunch of people and you say, well, I trust Len trusts this guy, and maybe if you're close enough in the web of trust, then you're an acceptable remailer operator. That sounds like an interesting idea. It's still difficult to get critical mass on that sort of idea, and there are some problems in it that we haven't worked out yet, but we're working on that. Yeah, pseudo-spoofing is a major problem in all of these decentralized systems. We need to manage the incentives well. It's a good start that in order to get more anonymity, you should run your own node, because then you trust it more. That's a nice idea. So dummy traffic. Alice is getting anonymity because other people are nice enough to send dummy messages. Why are they nice enough to send dummy messages? I don't know. Are they still going to send dummy messages? Are they going to remember to send dummy messages on that critical Tuesday when Alice sends her important mail? I don't know. Particularly if they don't know Alice's behavior pattern, which they're trying to cover, and they're trying to cover Alice's behavior pattern and somebody else's behavior pattern, you've got to send dummy messages that look like everybody. That means everybody has to look the same. That means we don't have that many users who want really strong anonymity. We've got a bunch of users who want weak anonymity. The people who want weak anonymity are not going to be willing to take the inefficiencies that are required for strong anonymity. So we've got a bunch of users who want different things out of the system. Suddenly we can partition it. These are the people who wanted strong anonymity. There are only 6 of them. These are the 10,000 people who wanted weak anonymity, but we don't care about them anyway. So it's unclear how to make the incentives work out. That's another difficult problem. Okay. So I'd like to let people customize the system. I'd like to let people have preferential service. If they need something really fast today, they can pay for more quality of service. Maybe they can pay more to get an even faster mail delivered. But if they're paying more and they're getting faster and you know they're paying more, then suddenly there are only 6 people who paid more today, and they sent mail to these 6 people, and it's probably this guy and this guy. So you can again partition the set based on how much people, based on what help people want and what efficiency and speed and service and so on. So we really can't let people do anything different from anybody else, and that's going to make a lot of them very upset if they're trying to have a usable system. So we'd like to let clients barter better. Mojo Nation was a system a while ago where you say, well, I've got 500 Mojo because I stored it up doing services for other people, and I want to spend it all right now to get a really fast download for this thing. But if you spend it all right now to get a really fast download, then you look different, and we can't have that. So the hordes in the coach seats are better off anonymity-wise than those in first class. Okay, an example, directory servers. So this is an extension of the stats servers that Len showed you last time. Basically, you've got a bunch of servers, or maybe one, that say, these are the nodes that are up, these are the reliability you're going to get out of them, these are the keys you need to use if you want to send a message through them, that sort of thing. We could set up just one, and then somebody would either knock it over, and then you'd never know any of the keys or who's or which remailers are in the system, or somebody would not knock it over and they'd just quietly go up and take it over, and then they'd give out the information they wanted to give out. So we need a set of redundant directory servers, one in Italy, one in Australia, one in the US, and so on. And they need to pass the information from each remailer around to enough of them and sign enough of them that a threshold can be trusted. And hopefully we can trust a threshold. So in this case, Mixmaster and the stats servers are really very separate concepts. Somebody wrote Mixmaster, somebody said, well, how do you know what they are? So they wrote a stats server. And somebody else wrote a different stats server, and they ping the network to say, well, these guys are up and these guys aren't up. But if we've got some clients that pull down a list from a week ago and they keep it, and we've got some clients that update every hour, then the directory is going to be different in those cases. And if a user uses a node that was just added to the directory, then you know that he was one of the people who updates frequently. So even if we solve that, even if clients have a uniform approach, basically they update every hour on the hour, and they never use a mix or a node or whatever that was just recently added to the directory, which is a reasonably good idea. There's still some attacks. There's the trickle attack issue. I send a message, and the node gets my message and says, well, this was probably sent recently, but I'm going to just sit on it for 4 days. And when I release it again in 4 days, then the directory is going to look different. If it goes to a node which is now very low in the directory reputation server, then it's unlikely that they would have chosen that. So it's probably the one that I just released. And you can combine this attack with an active attack of, I take the message, I sit on it for 4 days, and I knock down nodes that I hope it might go through. And then those are down, and their reputation starts to suck, and nobody in the right mind would use them, and then some message does. So you can correlate that way. So there's always going to be a tension between giving clients accurate information and not letting the adversary manipulate that. So, I've told you a couple of interesting approaches here. We might be able to build something out of the anonymity systems that we've got. Usability is a security objective. These things are really hard to use, and not just from a user interface point of view of how do I actually get the message sent, but why do I want to wait 6 hours? If I'm trying to have a conversation on a mailing list and remain anonymous, I can't wait 6 hours before my message comes out. I won't use the system. I'm not going to have as many users on the system, which means we're not going to get the anonymity that we want. So we need it to be fast, and we need it to be anonymous. And it's very hard to get both. On the other hand, we really need this stuff. Do you really want all of your communications to be logged and tracked and profiled, and they'll know everywhere you've gone and everything you've thought and so on? We really need to solve some of these things and integrate them into the applications we use in a way that is convenient and a way that is usable. That's something we're still working on.
Maybe many users don't want anonymity at all. Maybe they want pseudonymity.
So the point is, maybe users don't want anonymity, maybe they want pseudonymity. What do you mean by pseudonymity? Do you mean I have an alias that I use and I keep using it?
For example, rarely on Slashdot does an AC say anything that I'm interested in.
Okay.
Okay? I don't care if I know who the person is, but by having a consistent identity to tie it to messages, I say, wow, this person says things that I'm consistently interested in.
So the point is, maybe you do want to attach something linkable to your statements so people can say, well, that was the guy who said something useful last week, and he's got the same name now, and I don't know who he is, but I'm going to pay attention to it. Is that... yes, that
for commerce as well. It's their identity has to be linked to a monetary transaction.
That is that's a very good point, and it is totally separate from this point. Anonymity and pseudonymity are equally hard in this sort of situation. Pseudonymity is maybe even harder if you want reply blocks or something like that. You can get pseudonymity by using an anonymity service and attaching a name. If you want to get provable pseudonymity, then you get a key pair that you don't give to anybody, and you sign each message with that key pair, so you know that it's from the same guy. But yeah, pseudonymity is as hard to get in a strong sense as anonymity, because you need to prevent somebody from linking the pseudonym you use from the real name that you have. So it's hard enough to build a killer app. Very few people are doing it, and they're sure not going to want to put in inefficiency and make their users unhappy and make their system unusable in order to add anonymity. It's going to be really, really hard to get all this stuff figured out at once. We need to start thinking about usability. We need to start thinking about how to make the incentives line up right. We also need to actually solve the technical problems, because we haven't solved those either. So it's a pretty young field. Okay, so there's a point of light. A couple of other people and I have designed a thing called MixMinion, which is, it improves a whole lot over Mixmaster in a variety of ways. I'm going to be talking about that on Friday morning at DEF CON. And hopefully I'm trying there to take people from this is a forwarder, this is why it's not good enough, all the way up through this is the Cypherpunk remailer system, this is Mixmaster, this is MixMinion, and these are all the problems we haven't solved yet. So I'm happy with it so far. It doesn't solve all of the problems. Long-term intersection attack is unsolved. Abuse issues are unsolved, but it's something. Another thing we've been thinking about lately, and I'll get into this just a little bit, and then we'll go to questions. Synchronous systems. So I talked about mixed cascades. Mixed cascades are an example of synchronous systems. You've got a batch that comes in. It's 100 messages, and then it goes down the path, and it goes in its group at each time. And maybe there's a deadline by which a given mix in the cascade has to send all of the batch to the next one. So every 5 minutes or something, you've got to send it forward. Otherwise, you screwed up. I built a reputation system out of this a while ago, which said, I'm going to start identifying nodes that don't pass messages quickly enough. And you've got a deadline, and if you don't pass the message by the deadline, then you get a -1 on your reputation, and we've got reputation servers that track how frequently nodes screw up. So that's one approach. The length of the path would be fixed, so you've got 100 messages that come into the system, and they bounce around. Maybe they go through a synchronous cascade where it's a fixed route, or maybe you choose the path, and they go through whatever path you choose. And the anonymity set is based on the number that came in and the same number come out, and you're hiding in that group. So in a sense, it's plausibly deniable, because of course you sent a message, and of course somebody got a message, but you can't tell which one was which, unless you start looking at the sort of thing Len was talking about, where this guy is more likely to talk to that guy, or wait a minute, he signed a signature on that. That's no good, or that sort of thing. So we improve flooding and trickle attacks here, because a while ago I was talking about an attack where you take a message and you sit on it for 4 days, and then you release it, and the situation is different, and hopefully you can nail somebody with that. If you sit on it for 4 days, then the next node won't accept it. This message has expired, you screwed up. So you can't attack that sort of way. So synchronous systems are really nice if you can handle the high latency that you need to use to synchronize all of the systems. If we're trying to keep 100 nodes on the internet synchronized to 0.01 seconds, that's not going to work. It'll never work. You can't even get a message through in 0.01 seconds for sure. So you need to synchronize within 5 or 10 minutes, and we can't have that sort of latency for web browsing and that sort of thing. But maybe it's a good approach to use for mail down the road. And once we've learned a little bit more about Mixminion, I'm going to start trying to figure out how to introduce the concept of synchronicity there. Okay, if this stuff is cool, then you should consider going to the workshop that we're running in Dresden next March. I've got a URL up there. Okay, ask me a lot of questions. What can I elaborate on? Was there a design or, yes?
What are your thoughts on this technology versus cookies?
You're going to have to stand up and shout that louder.
What are your thoughts on this technology versus the use of cookies and web browsers for online shopping?
What are my thoughts on using this technology compared to doing online shopping and that sort of thing? You mean compared to as in for? What are my thoughts on using anonymity systems for online shopping? I think it's a fine idea. You've got to pay attention to the data anonymity, because when you anonymize your connection and then you say, Roger Dingledine, here's my credit card number, here's my address, then you didn't get what you thought you were going to get. There are a couple of companies that are working with UPS and FedEx to basically anonymize the actual address that's going on. And you can go to American Express and say, please give me a one-time credit card number. And that means that American Express can track you, but maybe if you trust that American Express won't collude with UPS, won't collude with the anonymizing system and so on, then maybe you're okay. It's difficult to scrub the data out well enough that people won't be able to track you with it, because maybe you're the only person who would buy a book on this particular topic from Amazon. But if you can solve those sorts of problems, it's a fine idea. And the concept of not letting everybody eavesdrop on what you do and track and profile and remember it is a very important one. Yes?
Is there research being done on applying this problem to instant messaging?
To what?
Instant messaging?
Instant precision?
Instant messaging.
Oh, instant messaging. Back when I was doing my thesis on anonymity, I really enjoyed the robustness issues of AIM, where you click, this guy's abusing the system, this guy's abusing the system, this guy's abusing the system, and once you've clicked it 100 times, then it gets kicked off. That's a side note for the accountability resource management aspect. Anonymity for AIM. Sure, great, wonderful. I bet you can use it with onion routing right now if you build an application proxy. You still have the data scrubbing issue that I was just describing, but you've got that in a lot of applications. Yes, there are a lot of peer-to-peer developers working on that sort of topic, and they're more than happy to say, well, sure, we're already kind of slow, and our users don't need the stuff to go that quickly. So we'd be happy to replace our direct connect call with your connect over onion routing call, and we'll treat it the same, and you'll take care of the anonymity. Yes, that sort of thing can be done. I imagine users of Freedom used AIM over Freedom? Yes, no? IRC, okay. So they had anonymous IRC, and it should be a pretty straightforward step. Listen to Ian's talk about instant messaging in a couple of hours. Yes?
When you were talking about onion routing, you were having a problem that you could do traffic analysis because you would have a large amount of data when you were requesting something, but the rest of the time you either didn't use up all your bandwidth or you could show that something was going on.
Yep.
What do you think the effect of some sort of random traffic creation, where you randomly, through whatever pattern, synthesize the traffic flow and then use that packet flow even when you're doing actual traffic, so that some of the time it's fake, some of the time it's real, but there's no real pattern other than what you're putting forth, and it gives you a much lower overall average of traffic through your network.
Okay, so the question is, what about traffic shaping? Traffic shaping is the concept of, rather than saying, well, you'll only ever, you will possibly send 100 kilobytes, so I'm going to always send 100 kilobytes. It'll be flat. Instead, you say, well, I'm going to have your traffic pattern look like a sine wave or something, and you will send exactly so that you're always sending the sine wave, and when you're low, then you're not wasting much, and when you're high, then you can send lots of data, and if you've got more data to send than you're allowed in the sine wave, then you wait and you push it on down and so on. Was that the question? Yes, that's a good idea. It's what a lot of people have been hoping to do. Onion routing, a couple of years ago, somebody said, well, how come onion routing doesn't handle traffic shaping? And I think Paul, the guy in charge of onion routing, says, oh, well, of course we do. We figured it all out. I've argued with him for a while since then, and we unfigured it out. So it's a good idea in principle. It's a great idea. It's difficult to handle, it's difficult to anticipate the amount of traffic you're going to get. It's difficult to enforce that sort of thing. But yeah, it could work. Another approach would just be to say, well, 100 kilobytes is the most you'd use ever. So you're probably on average using 10 kilobytes, so I'm gonna smack it at 10 kilobytes all the way down, and now you've saved 90% of your traffic. And people can't do bursts, but that's okay. And so is that seems to be a very similar concept.
Yeah, basically along those lines, but instead of using a set pattern like a sine wave, use some pseudo-random seed generator, like some PN code to generate your traffic and change it every day. So that, you can throw in spikes because there is no set pattern to what your traffic shape should look like.
Doesn't work.
Doesn't work?
Yeah.
Turns out from statistics on random patterns are amazingly powerful.
Yeah.
By looking at a handful of patterns where it's basically random, but then you threw in this spike because you needed it, and you just guessed that, well, he won't be able to tell that spike from a random spike. He can tell.
Yeah.
Statistics can pull out deviations from a random distribution.
It's fine if you actually pick a random distribution and stick with it, but in that case it's equivalent and easier to just do the constant thing. If you pick a random thing, and by random you don't mean random, you mean he can't tell if it's random, then you're on very thin ice. Other questions? How am I doing timing-wise? I've got a little while.
So what are you thinking along the lines of giving users incentive to anonymous networks? I mean, I don't have a particularly strong desire for anonymity in those things. It seems to me that you have a group of extremely paranoid people, and then a group of people with a very specific problem to solve, and those are your two groups that really need strong anonymity.
That's an awfully good question. I don't know the answer. How do you get people who don't want to be inconvenienced to inconvenience themselves for others? Education, maybe. There are people who wouldn't mind being inconvenienced, sort of, if it helps others. Education comes in a lot where you have to say, these people are doing political speech in a moral and good way, or whistleblowing, or they're protecting themselves from being stalked, or something like that. And it's the sort of thing that you want to help your fellow citizen out with. We have to make sure that people don't think, well, if I use these systems, then I'm helping the terrorists, right? A side note to that, one of the people in Germany is actually deploying a government-run web mix, where by government-run, I mean the government runs one node, and a bank runs another node, and a healthcare system runs a third node, and so on. And they basically have all pledged, we're not going to tell who the users of the system are, and we're not going to get together and break the anonymity unless the following situations happen. So this is a convincing approach from the government perspective to say terrorists aren't going to use our network for bad stuff. In reality, terrorists don't use the anonymity network for bad stuff, because if you're a terrorist and you want to communicate anonymously, then you steal a cell phone, use it, throw it in a ditch. You're not going to use these systems that are potentially vulnerable when you've got fine criminal activities already that work well. Other questions? Yes?
You look at anything that did multiple streams, Ghost Serve is a good product of that, where you'll use multiple proxies. And the first one that responds back to you is the one you use most often. And in this scenario, you get multiple paths out. The ones that respond back quickest are the one you use, so that kind of alleviates some of the panic in the system, but it also helps you generate noise and traffic for the rest of the system, because you need noisiness.
Okay, so I've got several responses to that, and hopefully my responses will clarify the question. The first response is you said, and that way you'll get noise, and you need noise. I don't just need noise, I need noise that looks exactly like other users. So I can't just say, well, send in a bunch of dummy traffic and your problem will be helped. Because it won't. People will think it will be helped and they'll feel safer, but they won't be. So the question was, what about systems where you're not really sure which path is going to be fast, so you try a lot of them and then you use the fastest one? First of all, if you ever send more than one message in Mixmaster, you lose. That might be a little bit of an overstatement, but you're developing a pattern that is different from everybody else's, and people who want to figure out who you are can do that. If you send 12 messages at once in different directions, or maybe in the onion routing system, you open 12 circuits through different paths. First of all, the adversary who owns, say, a quarter of the nodes is much more likely to be able to compromise one of those paths, any of the 12, than if you just opened one. So that's a dangerous issue. Another issue goes back to the reputation, you can't tell if somebody who's fast is honest issue. If I open 12 paths and one of them's best, there may be a reason why one of them's best. Somebody made it best for me. That might be kind of suspicious. I want to choose the path in a way that I trust, in a random way that I trust. I don't want somebody else to have an influence. And I already have the influence because I've got the reputation server that I go to and I say, tell me the nodes I can use, weighted by whether or not you think I should use them. That's a dangerous concept in itself. So yeah, what you just described is a trade-off between anonymity and efficiency, or anonymity and usability, or anonymity and user happiness. There are lots of trade-offs like that. And if you want strong anonymity, then you don't want to do the trade-off. If you want users, then you sure do. Yes?
Do you think some of these problems may be solved by the development of a new transport protocol, something that doesn't have return addresses perhaps, or something that acts more like UDP or ICMP to send data than TCP/IP, so that you don't have as much information about the same information?
Okay, so the question is, TCP and IP in general say where it came from, and that's potentially a vulnerability that you might want to fix. It is a vulnerability that we might want to fix, but the assumptions that we make on these anonymity systems are the links are probably watched, and you probably know it came from here to there. if you own anything around there. So I was thinking about this earlier in terms of the move from IPv4 to IPv6, because what happens when the source is guaranteed to be right and it was dropped otherwise, and we've got a hash and it's encrypted and it's authenticated and it comes from some guy named Roger, we're fine in that situation because we've got an overlay approach that we assume you can figure it out from one link to the next. But despite even that, then we're able to build an anonymity system from higher than that. So yes, you can get a little bit better, but I think if your adversary can touch the link, then we might as well assume he can see all of it, and he can see both sides. There are some systems that do that, like Triangle Boy and so on, that try to keep you from even knowing who you're talking to. You flood UDP somewhere and it arrives, and as long as it's a one-way connection, then you're fine. It's nice to work on. I don't think it's going to provide security on the level that we want. Any other questions? Okay, I'll let you guys go to lunch. Thanks.